what's come out so far is mostly cryptographic. So quantum mechanics is very good at certain cryptographic protocols. You've probably heard about it allows you to send information between parties very securely. That's already been implemented, actually. But there are other cryptographic tasks which quantum mechanics is terrible at doing. So bit commitment, it's an important cryptographic primitive, and it is provably impossible to design a secure bit commitment protocol within quantum mechanics. However, once we throw special relativity in, there turns out to be a very simple, quite obvious way of doing bit commitment, which is unconditionally secure. So to beat the protocol for somebody to cheat would be to break the law of physics. As well, there are new cryptographic tasks which they're inherently spatial, so they just didn't make sense before, but we can consider them now, and they're interesting, they're useful, and that's something else that's coming out of this work. So the particular task that I look at is called summing, and this is the simplest task. So what happens is we receive a quantum state that is based on a point x, and we're going to be required to place this quantum state at one of the coordinate points z0 or z1. And at the points y0 and y1, we're going to receive information about where to go. So at y0, we receive information telling us whether or not the state is z0, and at y1, we receive information telling us whether or not the state is z0. Okay. So we require that exactly one of these is selected, and we just ask, can we do this task with respect to where we actually receive the call? So the particular case of this that I'm most interested in is the case where these pairs are separated enough that Z1 is outside the future light cone of Y0, and Z0 is outside the future light cone of Y1. But they're close enough together that Z0 as well as Z1 are inside the future light cone of X. Okay. And what's so interesting about this case is that if we just think about special relativity or just think about quantum mechanics, you can do it. But if you think about both of them at the same time, then it's impossible to do it. So if we think about just special relativity, so special relativity with classical information, we receive classical information at X, and to complete the task, we simply copy it twice. We send one copy to Z0 and one copy to Z1, and then irrespective of where we receive the call, we'll have placed the state or the information at the correct real point, and we've completed the task. It's very easy. Now, if we just think about quantum mechanics, but forget for the moment about special relativity, we see that we can also complete the task. The strategy we just considered doesn't work, because in quantum mechanics, there's a very important and fundamental fact which says that we cannot copy a quantum state. So if I give you an arbitrary quantum state, you can't use two copies of it. So I can't send it to both, as I did in the classical case. It's still possible to complete the task. What we do is we take the quantum state, we move it from X to Y0, we check the call information that we received there. If it's telling us we need to go to Z0, then we move the state to Z0. If it's not to Z0, then we move to Z1, and this way we complete the task. So we move that specimens to the light there, but we're getting no special relativity, so that's okay. Now, it turns out that if you consider both quantum mechanics and special relativity, so you can neither copy the quantum state nor send things faster than the speed of light, this task is impossible. The proof is entirely obvious because we can do things like teleportation, error correction, allow us to localize the state, but it isn't too hard. So this is really telling us that quantum information in the Minkowski space has something new to say. If we didn't consider this fuller picture, we would have missed that this is impossible. But by considering the full picture, we see this. We see something to say. And useful as well. This turns out to be exactly what we need to design the secure bit commitment protocol. And in the context of my work, why I'm interested in this is because the question I'm trying to answer is, how can I move a quantum state through space? And this, or generalizations of this, are going to provide a nicely defined framework for approaching that problem. And we'll see that. So more general summoning tasks look something like this. We have a whole bunch of call points, each associated to a reveal point. Whereas a simple summoning task is in one spatial and one-time dimension, we now put them in 2 spatial one-time dimension or 3 spatial dimensions. And again, we just ask, can we do it or can we not do it? This is a particularly interesting example. The setup is such that we have this loop of connections, so it is possible to send a signal from Y2 to Z1, from Y1 to Z0, and from Y0 to Z2. Then the associations go the other way, so Y2 calls to Z2 and so forth. So we have this loop of connections. Now, if we were trying to do this task, and we're trying to do this just by sending the quantum state along some curve, we're not going to be able to do that. If you think about it for a bit, it's clear there. However, there's a way we can localize the quantum state which will allow you to complete this. So what we use is called quantum error correction. Upon receiving the quantum state at the point X, we encode that state into 3 states. And we perform this encoding in a very particular way, which allows us to reconstruct the original state from any 2 of these 3 parts. I won't describe how exactly that works, but you'll have to take it on face value that this is possible and not so complicated. So we end up with these 3 parts at X, and we send 1 part to each of the call points. And then at the call point, if we receive the call, we send that share to the associated endpoint. And if we don't, we send it along the adjacent connection. So this completes the task. It's not too hard to see. Say the call comes to Y2, then the share which is sent to Y2 will be sent up to Z2, and Y0 will not receive the call, so it will send it along the adjacent connection that's up to Z2. We end up with 2 shares over at Z2. We reconstruct the quantum state. We complete the task. Okay. Now, the second task we want to consider, and the strategy I use here also will prove to be important. Looks like this. The connections that we have are, you can send a signal from X to Z0, and from X to Z1, and from Y0 to Z1. And we ask, can we do this? So again, if we send the quantum state along the curve, it's not going to work. Also, error corrected codes aren't going to work. There's another way of delocalizing the quantum state which will allow us to do this task. And that's quantum teleportation. So before the task starts, we distribute an entangled pair between X and Y0. And upon receiving the quantum state at X, we perform a joint measurement on the half of the pair that's at X and the original quantum state. Okay. So after this happens, we get 2 things happen. Classical information comes out, and the other half of the pair, which is at Y0, will become a rotated version of the original state. So we then send the classical information, which of course we can copy, to both Z0 and Z1. And then the rotated version, which is at Y0, we send to Z0 for calls for Z0, and up to Z1 if it's not for Z0. And in this way, we end up with both classical information and the rotated version of the quantum state at the correct endpoint, which is correct, and we complete the task. So quickly, these definitions to state our main result. The causal diamond DI is the intersection of the past light point and the reveal point with future light start point. Those are the blue regions. We need to define some structure between these regions, which is that 2 regions are causally related. If there's a point in one from which we can send a signal to some point in the other. This is the main theorem. It characterizes exactly which tasks are possible. So a task is possible if and only if the following conditions are true, which is that every reveal point is the causal feature of the starting point. And the second one is every pair of regions has to be related, has to be causally related. So the necessity proof is quite easy. The sticking proof is the interesting thing. It tells you exactly how you can delocalize states. You can come talk to me on Sunday at the poster presentation. I'll give you the full rundown, or you can find it on the archives. So in conclusion, by every task represents a way of moving the quantum state through space-time. And by understanding exactly which tasks are possible and which ones are impossible, we see exactly how we can and cannot move quantum states through space-time. And so that's exactly what the theorem gives us. We've sort of solved this problem. And so when we look at distributed tasks, we now understand the quantum information that comes in, how it can be moved around, and we're closer to understanding these big tasks. The conditions are really totally minimal. They're just statements with no signaling and no cloning, which are the absolute most basic restrictions that you can get from quantum mechanics and special relativity. So I really like the theorem for this way. It's kind of beautiful. It's very simple. It's the easiest thing that could have been. And just the final point is that the error correcting code strategy with the three-loop task, that's novel to this work, and it hasn't been considered. I think it's very interesting, it's quite peculiar, and it may have future cryptographic applications that I'll be thinking about in the future. Questions?
I'm very curious at the moment, what are your next steps on this project? What are the next?
Well, I've been installed with Winchams for the last couple of weeks, and the results fairly nice. For the person who this work stems up, I got in contact with, and we're going to start collaborating. So I'll hear what ideas he has. But what I would like to do is kind of go through the whole papers that I read, talk about the different cryptographic applications, and think about those in the context of this new way to localize the quantum state now, this error correcting code strategy, and see if